Okay, so I'm Chris Smith from Elan Power Products, and a bunch of guys on the internet were asking a bunch of questions about the old Panoz LMP1 engine. I said, well, let's just make a video of it. Nothing secret anymore. It's old technology now, but we still do a bunch of these all over the world. Really, guys are vintage racing them. There's some in this country racing them. So this is one. This is actually George Crass's engine for his LMP1 car. It was purchased for Riley, and that's how you can see the water out coming out the front, whereas the Panoz version, the water exits the rear of the engine. So there's quite a bit of stuff to do to it to convert it from a Riley combo to a Panoz combo. But history of the thing, it's a 6-liter Ford. The bore stroke typically is 3/450 by 4/100. The program was originally started by Roush in like '96, and Roush made this sump, which is structural. I mean, this is about a 30-pound sump, built aluminum, and you can see this is actually what connects the car. So these big through bolts here and through bolts here go to the tub and go to the front suspension here. So this, we inherited, Elan Power, we inherited this from the program when we took over in '99. And after Roush had it for a while, Don sent the program to Robert Yates, and Yates ran this, and Yates commissioned, or Don and Robert Yates commissioned Zytec, which is now Gibson engines, to do this carbon manifold, and also run the Zytec fuel injection, which was really durable, really high quality. It just didn't have a lot of features. Pure alpha M fueling, not a bunch of corrections, no traction control, no very little gear shift control, but really robust stuff, but not a ton of control. So when we started this company in '99, late '99, we were tasked with building a bunch of these in a hurry, so we built the whole facility, inherited all these engines. But we didn't have a lot of the parts, so we had to source a lot of the parts. We had a bunch of blocks that we inherited, but a bunch of cranks, but we sourced all new parts. We ran Bryant crankshafts. Actually, we ran LAE Enterprises crankshafts first. We ran Carrillo rods, JE pistons. I can show you a little bit about that. But back to the structural part of this. The pan is structural, and also not pictured here, it's a carbon tint that makes the restrictor's airbox seal. But it's a really thick carbon fiber sandwich with honeycomb that's also structural. So it's about this long, connects the front of the car to the tub, and then this connects the bottom of the car to the tub. So the car is like when you say a structural engine, this is a complete structural engine. There is no car without this engine connecting the tub to the front suspension. So when we got it, originally came with Weaver Brothers oil pumps, and they were gear oil pumps. We had Bill Daly, worked with Bill Daly to design this pump, which rotates backwards. Basically, these are the scavenge pumps into these scavenge sections. It runs back through here, through this centrifuge, and it slings the oil out, in theory, so you're separating the oil from the blow-by and air here first. So this is a higher quality oil going back to the tank. And it can be put in the tank lower and gets back to the pickups quicker. It's really a game changer. This as far as oil quality in the tank, not being aerated, is a game changer. We still use this technology today. This came around about 2001 or 2. That was one of the mechanical changes we made, and then the biggest change we made was, back in those days we had to run Elf fuel that was about 98 octane, and these are 13 2-to-1. It was a pretty volatile fuel, big spread between research and motor, and so you really didn't know what you were going to get batch to batch. So we spent a lot of time and money converting all these to Boss fuel injection with the active knock. And we drilled, this head's not drilled, but we drilled through here into the combustion chamber, and we actually measured the combustion pressures real time. We mounted an encoder on here that was super accurate. I measured every, I think it was 100th of a degree. So we actually measured the cylinder pressure real time, identified knock, and identified debt. I call it knock. Identified debt, and then we worked on the frequency of that debt to understand it completely, and then honed in the knock sensors to identify that and retard the engine and keep you out of trouble. Also, in that time, these injectors, the original program had the injectors way up high, which is good for power. You know, it kind of, a little evaporative cooling, a little RAM charging, you know, it helps with power. But we also made these lower injectors that did the transitional stuff. So these would come on, it would idle on these lower injectors. It would blip the throttle on the lower injectors. But and they would fade away to like maybe 10% of the total fuel in the end. They'd run completely on these. We also did a lot of testing on fuel pressure and injector size, try to hone in on what's the magic number of, you know, open injector time. So we actually ran quite a bit of fuel pressure. These are 8 or 10 bar, I think they're 8 bar regulators. And then both of these, one of the cool things we did was we made sure that both banks of fuel injector would run the engine. So it was a little bit of redundancy. So if some portion of the loom quit, the engine would run fully on these or fully on these. But typically we ran about 90% of the fuel through the uppers, 10% through the lowers. And Bosch was a big fan of the big giant fuel rail to kind of dampen the pulses of the injector to the thing. That's why they have these big 1-inch ID fuel rails, upper and lower. And then the integration here, Derek Peacock was in charge of the program here, and he designed these fuel rails and little widgets to distribute the fuel out of this lower, which was pretty tricky to make a leak-proof deal there. And then we spent a ton of dyno time, because you gotta remember this was before drive-by-wire. These were 2 1/8-inch plates, so the tiniest little bit of movement of this throttle equals just an exponential amount of airflow change. So getting this manifold balanced and the ability to roll on the throttle well and evenly, we spent a lot of time making all this linkage. These shafts through here are split again here for a balanced bit in between pairs of cylinders. This was a really robust unit. Bill Gibson made this. Potentially Day Price Composites made the manifold itself, but the Zytec group designed and built this, and we had very little issues from this manifold being even glued together with the billet sections and the carbon runners. That worked out really good. It was a little bit tough to get it to run perfectly, but we came up with procedures that made it idle well, start well, and transition the throttle well. What else did we do with the Bosch? And the Bosch stuff, added a bunch of traction control to the car, a bunch of gear shift controls to the car. This was pre-paddle shifts. This is all load cell flat shift back then. But one of the weird things we noticed was compared to a lift shift is the way the actual rate of RPM change between gears was crazy. Now we were seeing 1200 RPM change in 40 milliseconds. So it sort of caused a little havoc in the valve train at first, but we got our head around that. But compared to a lift shift where you're lifting off the throttle to unload the dogs, it was really a big difference. Let's see, back to the base engine. Let's see what's inside. Nothing really fancy inside, really bulletproof stuff for the time. We worked a lot on oil consumption, and then what we learned is we replaced some liners along the way, and we learned that they didn't have much press fit. So at temperature, we were losing press fit, and then the liner thickness wasn't really thick enough to keep the bore rigid. So we went down a giant exercise of how much press can we run without splitting the aluminum between the cylinders, and will that help with blow-by oil control. And we really hit on something. We came up with a material, expansion rates, and put liners in it that really helped the oil consumption and ring seal. And then we fitted them all with that. And to this day, we hone every cylinder of aluminum for the exact press fit technology that we learned here. And that really makes a difference in all of our blocks today. What else? It's a Yates belt drive that they ran in NASCAR. It's a big wide HTD type tooth belt that works good. It keeps some of the harmonics out of the valve train. It had big cam bearings, potentially too big, because it's sort of the cam bore sort of invaded the liners. And in hindsight, we'd make them smaller now, because at the bottom of the liner it got sort of thin because it wasn't supported by much aluminum. So we had some trouble with the block flexing down low. So with 3/450 stroke and this little short deck that we ran about 185 crankshaft to the deck, the piston comes out of the bottom of the bore. So we had to work pretty hard to come up with some honing techniques to get the bottom of the bore sized when it was trying to flex out of the way. And really, in hindsight, that was probably because the cam bore was too big for this engine, being aluminum. We did a bunch of spintron work with comp cams. We ran comp cams, camshafts. We ran Jessel 903 dog bone lifters, which are sort of old technology now. They run keyed lifters now, but they were good at the time. They were pretty robust. We ran, this is loose. We ran T&D rockers, all different kinds of ratios, aluminum. Nowadays we probably run steel. This is pretty neat. This is main oil galley here up over spray bar, and each one of these springs has this spray bar has a hole drilled in it that sprays on the valve spring. Does a good job lubing the valve spring. This is an old flat wire damper, so it's double the flat wire damper. I think these are actually ISKI 9965s. It's like an industry standard. But with a smooth enough cam, they would run 28 hours. We creeped up on pretty close, a little over 700 intake lift, and we had about 660 exhaust lift. Camshaft was like 254, 258. Because you got to remember, this thing was all done at 6,800 RPM. Shifted about 72 because the restrictor would just clamp it down. What else can we talk about? One of the things that, here's one of the cylinder heads for it. One of the things we do now is we had some trouble with unleaded fuel and these beryllium copper seats. So these are 1 mil seats, and the beryllium copper now, and on this one, we run cast iron seats on the intake with chromium nitride coated titanium valves, and that's a bulletproof setup. We run a ton of exhaust seat width. This is a 2 mil seat. Kills flow a little bit, but so what? It pulls a lot of the heat out of the valve. Titanium valves with narrow seats, and when you put them in traction control conditions, knock control conditions with a bunch of retard, the EGT will routinely go to 900, 950. So the titanium valve doesn't like that. So the big wide seat kills some flow, but it works okay. We ran 45-degree seats on these. Later we ran some 50s. The heads were machined by Don Lazito, Ultra Pro machine. And then when we got them, we worked a ton on the seats, the seat angles, the valve shape for reverse flow, really. It was not about forward flow, but how the thing behaved, after bottom dead center, because we ran quite a bit of seat-to-seat duration. The camshaft was only 254 on the intake, but it might have been at 6,000, it might have been 310. I mean, it was a really gentle ramp shutting. So we had some valve hanging open that we didn't want. So to combat the reversion, we worked a lot on the valve shape to trap a little more, and that worked out. We made some progress with that. Because you got to remember, these things at peak power, you're like 820 millibar in the air bottom. So 18% of the atmosphere is gone. So normally when a cylinder would continue to fill, it doesn't happen because the atmosphere is not there to begin with. So reverse flow, anti-reversion techniques in the valve job and the valve were a big deal for us. In the pistons, this is pretty typical of what we ran back in the day. We wouldn't do this now. The rings were pretty thick. I think this was a 1.2 top, 1.5 second, and then a 3 mil oil. And we tried oil control. One of the things you can see is the pin invades the oil control ring, so it basically makes the oil control ring useless. We would try to avoid that these days. Everybody would. But really, in this package, you need so much stroke in there that you really can't avoid it. So nowadays, we would run thinner rings that would conform more to the bore. Back then, there was a lot of theories about rings taking heat out of the piston. Now we spray, 5 gallons a minute of oil at the bottom of the piston, so that's how we're getting the heat out. And we would also run a Napier second these days. Back then, they really weren't popular. Now they are. But this is pretty, full-on old school skirt design, base design, cam design. But they were pretty robust. We hurt very few. And you can see even at 13 to 1 with these, I think these heads were like 51 cc's. At 6 liters, we were still a flat top piston, which is always a plus. And that's all the pocket it needed for a 254 cam in an 107. Another neat thing that we thought worked at the time was this is the old school Triller rod. It's 5/460 long. It's this. Look at this thing. I mean, this thing can make 1,000 horsepower on its own. One of them. We never changed these. But one of the cool things it has is an EDM hole up the center through the pin to oil the wrist pin. There's some thoughts that may or may not work. And then it was pretty tricky that we didn't pull the oil off of the highest loaded section. We pulled the oil off over here and then transferred it over to the EDM drill hole through the rod. Nowadays we wouldn't have a bushing in here. It'd be a DLC pin in here. This is a 2-inch Chevy journal, like a 302 or 327 Chevy. Mainly because it's such a common bearing. It's really common in racing to run in V8, big giant 7/16 bolts. What else did we do? What else did we have problems with? Oh, one of the things is these blocks are these through holes into the deck. They're in water. So, we have, you can see there's sealer under these. There was sealer, they were Loctite in the block. A lot of stuff try to control water. Nowadays nobody would make a through hole into the water through a stud, but this block is fully open, top and bottom. All the stud holes go into water. We had to put sealer in this and that, and sealer around the gasket to try to keep the water in the engine. What else? Power. They made one of the things about a restricted engine you have to realize is you need to make the best run. Like on this, we knew that really we were going to get clamped down about 6,800 RPM, and everything about it is designed to make the best running 6,800 RPM engine you can. So unrestricted, maybe 700, because the size of everything is not designed to run high RPM and high power. It was designed to run on that restrictor. So we ran 230s, 232s, I think. Then we made 625 horsepower, and then they kept clamping us down. I think they actually got us down to like a 30. I think we made about 2 times 30 mils. I think we made about 580. And it's funny, we have stuff in the shop today that runs on a 30 millimeter restrictor, and we make about, and it's half the displacement of this or a little less, and we make about half the power. But it was a great program. People around the world like the way it sounds. It just thunders. It's pretty straightforward. There was just a lot of development to make it run well, because the way it drove, the traction control, and we really didn't go crazy with the mechanical like we would today, because in 99 and 2000, the technology, there wasn't really that much technology as far as how light you could make stuff. Matter of fact, to nerd out, this is 1840 bob weight. We've made some later editions of this that were in the 1600s. So, it's a 10% lighter parts in the rotating reciprocating assembly. So, we're glad we still make them. We're glad people like it. You know, Don's no longer with us, but this is his legacy. So check us out on social media, lawnpowerproducts.com, Facebook, Instagram. That's it.
Awesome.